is a bit more complex. We have on site some of the people that actually contribute to centers of excellence. So please take the stage yourself. You can use the microphones here. I understand you have some presentation material. As far as I can tell, we are putting this up. Do you have presentation material as well? Yes, it's there. So please on the stage or you have not. I think on the remote, we also have Stefano. Stefano, you're there?
Yes. Yeah.
Thank you, Stefano. Apologies for the overrunning schedule, but we appreciate having you here. And perhaps from the people on remote, perhaps Matteo would like to attend this part and perhaps reiterate his position on co-design.
I'm here if needed.
Yes.
Hi.
So just for completeness and so that we have this on the recorded session, perhaps once each of you starts with saying his position, perhaps you can introduce yourself and actually say what is the particular center of excellence, one or more, that you are active with. Okay, if that's fine. Stefano, is it all right if we start with you being remote?
Yeah, sounds
yes. Yeah. So. So we started to see your screen, not yet full screen, but we're getting there. Yeah.
Yeah, just Zoom has too many small gadgets.
You're doing well. Don't worry. You got it on first try. Thank you.
So good afternoon, everybody, and thank you very much for this opportunity. I'm here today to talk a little bit about the Plasma Pepsi Center of Excellence and our engagement with the co-design, specifically with API devices that have been discussed. So just to give you a few quick facts about the project. We started in January 2023, and then we are finish up basically December next year. We have an overall budget of 80 million, and 50% is co-funded by national funding. So I'm working at the KTH. My name is Stefano Marchidis, and I'm the coordinator of the project. In total, we have 10 partners. I put it here in bold all the partners that are specifically working on the co-design part of the project, specifically on testing, give feedback to the project about using large plasma codes with the API devices or simulators of the API devices. So what the project is about? So the project is science driven. So is driven by try to tackle three main challenges. One is simulating fusion, specifically in the magnetic confined devices. And the second major grand challenge is to model in order to produce very compact plasma accelerator that can be used, for instance, in hospital to treat cancer. And the last grand challenge we have in the project is looking at modeling interaction solar wind, the magnetosphere, specifically for problem related to space weather. How we can make prediction about dangerous phenomena that put in peril some of the technology, human technologies, such as spacecraft, satellites, that can be damaged by the solar wind. As Matteo mentioned today, so we use the goal here is to use exascale a system to answer the question that the scientific question that we have here. We have a roadmaps, we have a gap analysis that have been updated with the goal of solving these questions at exascale. So the vision of the project is to push flagship plasma simulation codes. We call this flagship because these are a reference plasma code for the computational plasma physics community that have demonstrated petascale capability in terms of scalability and has a scientific need to use exascale system that is answer this science question. We do that through two major approaches: grand challenge, performance optimization, GPU porting, and also co-design. How we can computer scientists, computational plasma physics, domain physicists, and also people working on API devices can come together in order to improve the performance of the code. We have two codes. We have four codes. Gene is a fusion code. Bit is a particle cell code for studying the interaction of plasma material with the wall. Picon GPU is for laser, and the Blasiator for the plasma, space plasma, and space weather. I will just say a few words about the added values of having co-design. Within the project, we have a specific work package that is devoted to co-design with the API devices. So we have one task on the API processor, the SIPR, ARM processor, and one task on the EPAC RISC-V accelerator. So what is interesting here? Well, the major interesting part, and I think the added value is a two-way part. So one, we have people working on the hardware part that are they have the possibility to experience the large code, real world code that are being used in production. So typically, the full code is not used, but the experience that computer scientists have, with a full-fledged code to work with the full developer team in designing some meaningful code that represent the major code. So that's one important aspect. The other important aspect is that we had the challenge as a project is how to define a methodology, this two-way methodology that can keep in the loop both hardware and developer, software developer, and application developer. So the project itself, thanks also for the work package 2, looking at co-design technology, was looking at a top-down approach with performance monitoring unit analysis, application profiling, and then giving feedback to the application. So we have a number of results. I'm not really detailing here. I just want to point it out. It has been very fruitful. From the RISC-V APAC accelerator, we have a similar methodology, including emulation, hardware runs with counters, and then a cross-architecture comparison. So here the outcome is really insights for the API hardware software and optimized code paths for future Euro HPC system. I just want to finish on my presentation, looking at the more at the requirements and what is actually is important, at least looking at the Center of Excellence itself. So we're looking at a lot of vector compute, either in the form of SVE or long vector RBV for RISC-V processor. And here the compilers technology, they play a big role. Data placement and data movement becoming more and more important. So it was already important before we caches, but now with the HBM together with the DDR on the same node, it needs us to think about, you know, what you need to be in an HBM, DDR, and what are the different trade-off. As a performance tool, when it comes to application, are you know critical for understanding, but also for application developer. So rich performance monitoring assets and you know profilers and you know all the software stack that regarding the tooling part is becoming more important. Together with the compiler part, there is important you know, portability issue, but also performance portability in the project. In the Plasma Pepsi, we have the Alpaca performance portability layer. We also did work to port for instance, RISC-V backend. Interconnect are important, but is becoming extremely important for the data processing part. And we need to realize that many of these exascale applications are becoming more and more you know, fragmented. They're not monolithic anymore, but they might comprise a different part running in different part of the supercomputer require very high bandwidth transmission. For instance, today we are talking about also AI integrated in the code themselves for the data analysis. We have a few experiments where we show the scalability is not as good as expecting, mainly due to the fact that we need to move back, you know, back and forth quite a lot of data. Finally, also the application, the Plasma application, need to change to you know to address some of the new devices capability, especially when it comes to reduced precision, FP16, and also matrix engine like Tensor Core. As a project itself, also we are looking at some of the things that have been mentioned today, you know, pathways to integrate accelerators, reconfigurable computing, and including also a quantum computing technology. And this is the last slides. I'm happy to give a room to the next panelist.
Thank you very much, Stefano. Perhaps we can have space represented by Lubomir. Yes, I think everything is on the desktop area under a folder named Centers or something. Okay. Yeah. Perhaps give it a go. Day3, not yet. Not pretty sure. Isn't. Apologies for the delay. We're, as usual, looking for the files. We explained in Greek the situation. Why is it empty? It is empty. This is what I said. Don't worry, we get it done. I'm pretty sure I saw him too, but where did he drag them? No worries. Okay, they are still on the drive at least. And okay, more vigorously this time. Okay. And we have all the technologia. It's a brief intermission. Let's get this one. Oh, okay. Otman, you are synchronized with okay, okay. So, okay, yeah, I know your involvement, but it's okay.
And, attends, c'est pas la bonne version, hein. Ouais.
The next thing after where the files are you using the proper version?
So you want to change? I just want to check if it's the right version, but because whoa, no, not the one.
So is the wrong version?
No, it's my fault. It's the wrong version. So we can go with the max. I can do the max and we'll do space after that.
Oh,
If the max is the right version.
okay, so we'll go with another one until they send me the correct one. So. Yeah. So max 3, this one?
Yeah, max 3. Yeah, short presentation. We'll switch side.
You would send me one?
What matter?
Okay. So I will take this. Let me share again.
Okay.
You ready?
Yeah, thank you. So welcome everybody. So I would like to say a few words about the Max Center of Excellence. So the Max Center of Excellence it started at the same time. It's all the COEs that are currently running started at the same time. It's a 4-year project. We're right now entering the last phase. We have a review next week of the Max. So essentially, Max is a sentence related to the code for the material science. So we have these Max has these 5 codes, which is the Quantum Espresso Yambo, CS Staffler, and the Big DFT. So pretty much those are the ones that we call Max the lighthouse codes. And one of the key goal, of course, is to improve the scalability and port these lighthouse codes to the current Euro HPC pre-exascale and potentially the exascale systems. We also have a work package that it's forced on the exascale workflow. So essentially controlling multiple exascale, multiple petascale simulations into a workflow that it's controlled by special tools to solve some grand challenges in the material science. That's mostly the related to this work package. So what is related to the co-design and really explore of the advanced technology is a work package 4, where most of the technological partners are involved, and co-design is mostly carried on by our colleagues from Eviden and from Cypero. So we just you want to take over?
Yeah. Thanks. So I'm presenting this work on the behalf of my colleagues that could not come here today. So here is a bit of the results that have been produced by the co-design work package. So top left are some studies about the benefits of HBM versus DDR. They have been done on the Sapphire Rapid Intel CPUs that are the only CPUs available with such technology, and they are, I mean, a technology very close to what the Cypher CPU will embed. We can see some significant improvement thanks to using the HBM on some of the applications, and sorry, and some a bit less significant on some other. We also can see on the top right that some optimization that have been done to improve vectorization on SVE actually also brings improvement on Intel or AVX vectorization vector instructions. So that goes in the same way that what Filippo presented on what they did on the VEC, that brings the same improvement on Aurora or whatever Intel CPU. And here the big table is the status of the studies. So vectorization studies has been completed, and HBM study also. We are still waiting for RIA to actually complete the study if it comes before the end of the project. And in the bottom, I mean, it goes in the same way as what was in the table here. We optimize for SV, but in the end, we get the same performance when we focus on Neon because they are the same size on Grace. They are both 128 bits. And we didn't see much different in the Quantum Espresso application. We want to print tool.
So this one of the evaluation that we did in the Max, and actually this is also part to the code is developed under the Max, is that if you do the HBM studies, you either decide that based on the NUMA control, everything goes to the HBM, everything goes to the DDR. You can go a bit further. We have developed a tool that can pretty much take individual objects and place them into one or the other memory. Decision which objects to take can be done based on the profiling, and then pretty much we also have some exploratory studies that because it's not only individual, but also the combination of the objects. If one is in the DDR, the other is HBM. The other that is in HBM could have been faster, but as soon as it's reading also data from the DDR, the combination also matters. So we have developed a tool that is trying a different combination of the individual objects placed into the DDR and to the HBM to find the optimal configuration. So the goal would be that, for instance, you have a use case that your HBM is not big enough, so you cannot fit everything into the HBM. So you decide which objects you put into the HBM with the limited size to get the best performance. And it's pretty much shown for the Quantum Espresso in this particular chart where we can see the speed up using the HBM memory. Here it goes from 1 to 1.3, so 30% increase. And really, you see that if you find a right group of the objects, you can get to the full speed up that is given by the HBM, which is here at 1.0 means how many objects are put into the HBM. So 1 here means everything is in the HBM memory. So you can see that just placing half of them, you get to the same performance, and you're saving half of the memory. So this tool is developed. We're going to use it to explore all the applications in the Max, and it is essentially an open source tool that can be used by others. So it's just in quite early development stage. So warning. So this is pretty much the requirements that we serve. I mean, one of a big part of the work that we did in the Max is really extracting the mini apps out of this big complex application, because sometimes it's not even possible to run them on some advanced, some cutting edge hardware. So this is the big part of the work that we started at the beginning of the project. Some mini apps were existing, but we're extracting address. You've seen that the software stack that we've seen, it is there. We were able to compile and run the applications on the ARM ecosystem, thanks to the fact that we have people from Cyper. The Cyper is part of the consortium. They were able to do the evaluation of their compiler, which otherwise we wouldn't be able to get there. But the thing is that the features of the compiler significantly improves the application owners willing to go to that platform. So the need for robust major compilers is very important for them. We also did a lot of the testing for the HBM. We see that for max codes, the performance gained by the HBM is significant, but as the data structures can be large beyond the size of the HBM memory, the smart placement is needed, to use the HBM memory optimally. And the last which one you added?
Yeah.
So I'll let you comment on that.
Yeah, I mean, it's what I said on the two small arrays. Optimizing for HV is the same as optimizing for AVX or Neon or maybe VEC. I mean, we didn't experiment on RISC-V within this project, but developers should focus on vectorization, not the name of the vector you are using. Yeah, that's it. Any question, or should we move to the next? Yeah, okay. Well, go with easy ways, I guess.
Okay.
Yeah. Online, can you see the slides for easy ways, or is it still Max?
Yes, we can.
Okay, thank you.
Thank you.
So Easy Ways is a COE focusing on weather and climate applications. So again, like Max, there are several partners with several work packages involved. There is no specific work package for co-design. But within work package 1, we actually focused on designing a benchmark suite. I will talk a little bit about it after that. In the project, we also provide services to application developers and scientists to help them optimize their application. So this leads to several nice results. I mean, it's a bit out of the topic here, but still worth mentioning. And so yeah, the work, the result I present here are mostly done in the work package 1. So what we developed within Easy Ways, and also it was initiated before in the Escape project, is the HPCW benchmark suite, high performance climate and weather benchmark. So the question arises after the evolution of, after the creation of HPL, then streams and HPCG, are the benchmark result of this, synthetic benchmarks relevant for ranking HPC system nowadays, especially for weather and climate application. The peak floating point capabilities of the system is not always relevant, because there are sometimes a lot of communication, like all-to-all communication on the whole system. Then low latency communication is more important than floating point in some part of the application, of course, not everywhere. So the idea was to design a benchmark suite that represents relevant and realistic workloads that represent what is running in production for weather and climate application nowadays. So we released the version 3 this summer. It's the first open source release of this benchmark, and we will try to push this everywhere we can. It's already involved in some other international collaboration with Hanami with Japan and Ganana with India. BSC has been working on porting some of the dwarfs from IFS on the RISC-V at BSC. They are all running with vectorization for RVV. I'm not sure about the version. They are also experimenting on the Banana Pi clusters they have over there, and still working on implementing and testing OpenMP there. Of course, we did some experiment on the available ARM system we had at end for this, and this is some result comparing Graviton 3 with the Grace system. So for API feedback, one of the main results here is that having application-specific benchmark to design future system appears to be relevant, because just having a lot of flops is not always the best, depending on the application. As previously said in other COEs, the ARM software stack is getting there. We still need to port from time to time, and Intel's compiler is still the best at vectorizing, but applications are running, and usually it does not need that much modification to get the same vector ratio, just exposing a bit better the parallelism. And the same for RISC-V. So this is from Roger Ferrer from BSC, the last comment. He did the experiment. It's the same for RISC-V. I mean, the software stack is getting there also. And the vector extension helps getting performance. Yep. And we can move to the next one. You want to, tu fais cheese d'abord, et comme ça j'envoie les slides pour Space. On va les recevoir là. Viens sur cheese d'abord, et puis on va les mettre après. Up, and when you click, it's yeah, here. So you have it on the flash. Space. No, I don't have it on the flash. We are not allowed to use flash.
So I will present the CHEES COE. Well, CHEES stands for Center of Excellence for Exascale on Solid Earth. So it's about forecasting geohazard. And I'm presenting this COE on behalf of my colleagues, and who were not able to attend due to other meeting. So CHEES is gathering 16 partners around 7 countries, and sorry, laser pointer, yeah, it's here. So and the work is fairly distributed across these partners, especially in research. So sorry, research. We are all involved in this. So we are 2 private companies. I'm belonging to one of them, so Evident. And so the COE is driven by science, and it's covering geohazard as seismology, volcanology, tsunamis, and other components that are important on this, like coupling physical processes. Because, you know, when you have an earthquake, it can create a tsunami. So CHEES approaches the exascale in 3 ways. Capability computing, capacity computing, and urgent computing. So capability computing is it's solving huge problems by parameterizing or reducing the parameters. And so scientists are trying to obtain results for nice results that should be obtained at exascale, but with petascale mean of computing. Capacity computing is solving several individual problems on petascale machine, but that should require exascale machine. And urgent computing is to compute in a strict amount of time. For example, just after an earthquake, you should know what could happen next. Okay. Some things that were required in this COE is that scientists or application developers should develop mini apps to make a benchmarking suite to make easier the co-design of the hardware with these domain-specific applications. And as for the previous the previous presentations, we did the same workflow in the co-design. I mean, analyzing vectorization on x86 first CPUs to check if vectorization is good on ARM. We also tested the HBM on x86 processor because, as you may know, it's the only processor which HBM available, so namely Sapphire Rapids. And here you can see that the performance are going from 8% on only one compared to DRAM. Performance are improved by 8% to up to 44 or 45%. And in average, it's 15 to 20%. We also then checked how the code was vectorizing with on ARM on SVE, and we also checked the energy thanks to tools also provided by IT4I. And we also took the opportunity of looking at the code to see if there is some room for optimizations. So this was in the framework of UPEX. In the framework of UPilot, and this is unfortunate that Filippo is not there, but they were able to compile some of the code on RISC-V to check vectorization on an emulated part of the RISC-V, and to run this on EPAC. So as you may see, green boxes says that it's okay for this code, but for some of them we don't even try because of the unavailability of the code or lack of time to do this. And red boxes mean that there was no room or it failed to do this job. So I'm going quickly to the let's say conclusion or what is required as a co-design. So it is very important to have domain-specific benchmarks to ease the decision-making for co-design. Otherwise, it is required that we execute a huge application with huge data sets and with irrelevant part in the code, like checkpoint restart, or if it is not applicable, of course, in co-design activities. We can see that memory bandwidth is quite important, but is it really important to have only improvement of 44% of the code? Maybe yes, maybe not, but maybe yes in urgent computation. In critical situation when geohazard happens. Having a maturity of the software ecosystem is really critical because we'll talk about this later in space, because the workflow is the same. But we compared GCC vectorization against LLVM vectorization, and GCC is still faster. I don't even talk about Intel compiler, because we have no, well, we cannot modify it. But LLVM is going more and more mature, but not at the level of GCC yet. And sometimes the toolchain is failing compiling the dependencies of some codes. So with LLVM, I mean, because sometimes GCC options, requirements are hard written into the compiler toolchain. And last topic, which is one I think the most important, is that collaboration is important between application developers, HPC and AI experts who know well the applications, and some at a certain level the system and its environment, and the hardware developer is, yeah, it's something really important for the success in such a project. So thank you. There is one more.
We consider this the anchor by audience request.
Mhm.
Thanks, Paul. So it's me again. Now I'm gonna present the space, the center of excellence. So space is essentially a center of excellence around the astrophysical and the cosmological codes. We are these are the partners. Essentially, there is seven codes that are developed within the space. So these codes are pretty much owned by University of Oslo, Goethe University, K11, CNRS, and INAF. Yes. to support these codes, there are technological partners, and the University of Torino, which is the coordinator. The code developers are supported by technology partners, which are the Engines-Soft, Eviden, E4, and the supercomputing centers, which is Cineca, IT4I, and the BSc, where the BSc here is mostly focusing on the scientific visualization of the data that are results of the cosmological simulations. So these are the partners of the space. As I was saying, there are 7 codes. There are 3 codes that are particle-based cosmological simulation, which is OpenGadget, Ramses, and the Chang'e. And there are 4 grid-based codes, which are the IPIC 3D, Pluto, Phil, and the buck. So these are the 7 codes that we have, and essentially for each of these codes for each of these codes we did this study that Otman is going to talk about, because he was one of the experts doing the co-design studies.
Yes, so thank you, Lubomir. Yeah, this is almost the same workflow that we did for the previous series. It's comparing the execution of each of the codes by storing the data exclusively into the DDR versus storing exclusively the data into HBM. And we noticed some gain around, for some part of the code, around 2-3%, or between 20%, roughly. So again, does it worth the cost having HBM for only 20% of gain? That's not me to give the answer, but to people decide how to spend their money. And another thing is to compare the maturity of the software stack and essentially LLVM to know if this new compiler that should, let's say, replace maybe GCC, and on which NVHPC, One API, or the AMD CL compiler suites are based, is mature here. So where there is okay, the code compiles, and so it doesn't compile on 2 of the codes because of failure into the with the dependencies, the library on which these applications depends to. So LLVM, as a conclusion, is not really mature on ARM. Another thing we did is to compare the vectorization on the ARM CPU by compiling with GNU targeting Neon microarchitecture and SVE microarchitecture, and by compiling with LLVM targeting the same architectures. And we can see with the green line, highlighted line, that a GNU compiler is still faster than LLVM because time to solution is short, is the shortest one, and that Neon and SVE on. So this was done on Grace CPU. That Neon and SVE, well, here, in fact, SVE is takes a longer time than neon. So I don't know why, but this is the case. Another thing that was done is energy measurement, and I will let the floor to
Okay.
Lubomir.
So for the energy, we pretty much took the co-design platforms, which are the NVIDIA Grace Sapphire Rapids, and we ran the tests on the DDR on the Sapphire Rapids, just placing in the DDR, just placing in the HBM, and on the Grace, trying to search for the optimal configuration, but also evaluating the impact, the energy efficiency for this platform. So we can clearly see in these slides that if we express the energy efficiency in terms of megaflops per watt hour, so that the ARM-based processor, the Grace CPU is much more efficient. So comparing to the DDR and the HBM memory, and as the HBM memory is providing better performance, it does have some impact also to improve the energy efficiency. But there is a significantly better numbers in terms of the energy efficiency goes to the Grace CPU. We also do a tuning optimization, how to tune the hardware to provide the best energy efficiency. And in the first row, it's without really affecting the runtime, where the runtime is the second number. And we also see that if we take a Grace CPU with that, we can save a much more energy than comparing to the Sapphire Rapids by just tuning the frequency of the processor. So even so, the numbers that I'm showing here are actually not running the default configuration, but running this configuration where we search for the optimal configuration without affecting the runtime. So this is what you would expect. So that's another aspect that we evaluate, that the ARM platforms has a significantly better energy efficiency. So Otman, do you want to comment on this? It's coming
well,
from your work.
Yeah, so I would say same conclusion than before. So memory bandwidth is important for half of the applications, but on the other half is don't gain so much with it. We had a look at the codes. I didn't talk about this, and just to see how they can be optimized and utilize better the vectorization, not only AVX but SVE and so on. And they need a big refactoring because they need data reorganization. So everything is all about data. As maturity of the ecosystem, we have seen that this is still critical because LLVM is not widely used in the landscape of the libraries and dependencies for some of the applications. And same conclusion as before, collaboration between all of us is important because sometimes we are not application expert from the perspective of the HPC and AI experts. So we need application developers, and we need also hardware developers to better understand why we have bottlenecks during the execution of our codes, and hardware developers need also us just to understand how we use the hardware. So that's it. Thank you.
Okay, thank you.
Thank you all for these summaries. I know they represent quite substantial effort from each of the COEs that were briefly presented today. Etienne and I were saying that we see some common findings in terms of the recommendations that I think are worth pointing out. For example, I do see a concern about the the progress or quality of compilers, some of the compilers, vectorization capability, vectorization efficiency. There is a concern about memory resources available. A point about vectorization that, okay, it's important, but it's not so much one vendors or the others, is so much, rather it's more fundamental, if I understand, it's to make the code amenable to vectorization benefits. So I guess this is where the substantial effort within the COEs goes to some extent, but also a bit disturbing that we have applications. In the last presentation, it was Ramses mentioned as an example where substantial effort yields somewhat modest benefit, which probably points to a mature code that is reaching the point of diminishing return. So would you consider a direction, any of you perhaps can offer its own offer, also the people on the remote connection? Do you see that we are now at a time where it's worthwhile investing effort on more radical changes, code design that we're calling this code design based on profiling, iterations on the codes, etc. But would you consider, let's say, drastic changes, I don't know, in the numerical libraries being used, in the data structures being used, let's say programming environment changes, or even custom-built machines? Would you see this as a worthwhile next step in the evolution of your respective domains? It's an open-ended question. There is no clear black and white answer, but I would appreciate doing a roundtable about that.
So I will, one point of view that we see in the space, and that's actually a more problematic one for this particular audience, because one of the output of the deliverable is that you have to do like a major restructurization of the code to gain, let's say, 30% speed up. At the same time, being a center of excellence, the key role, unfortunately, is not the co-design. It's really deploying the codes on the Euro HPC systems, and the biggest systems do have GPU accelerator. So there is the biggest pressure of the COEs is to deliver the code that is going to run on these huge systems that are already procured and that are operational, and we have to use it as efficiently as possible. So taking this into account, a lot of the code developers are forced to really focus on porting their code to the GPU accelerators. And of course, yeah, that forced them to also reorganize the data structure that would be the organization useful for the vectorization. But if we provided them with the results from the deliverable, you know, this is the potential that you can gain by the optimization. Eventually, by the end of the project, only a subset of the codes is going to be working on the vectorization. The others strictly put their all the effort, all the manpower they have to really deliver the code that is going to run on this production system, which is it going to be the most important point for the final review of the project.
Yeah, I can comment a bit about the vectorization effort and the specialization. One fact is scientific code is moving really fast today, still moving really fast. We discover new ways, scientific discover new ways of modeling our world, our universe. They use different numerical methods to model them, to simulate them. Sometimes they come with an old way, an old numerical method to simulate something they observe that's new. Sometimes it's a new numerical method that comes, which is pretty rare. And numerical methods, sometimes they go well on vectors, sometimes not. Sometimes you need special hardware. And because it's moving fast, it's hard to say we can specialize today. There are some old methods that have been optimized a lot and that you can specialize a lot. I mean, typically it's not an application that's used in HPC. Typically the Bitcoin mining, I mean, it has been optimized to the ground, to ASICs, to whatever. And because it's not moving, it's the same hashing function that's executing always the same. And for HPC, it's not applicable yet because it's moving too fast at the science level. That's for the COA I've been working on. And even if you stay at general purpose processor and AVX, SVE things, vectorization instruction set, most of the time nowadays, after 20 years of x86 dogma, as I heard before, scientists do not want to be vendor locked again. So they don't want to program interesting things into their code because they want it to be portable to RISC-V tomorrow maybe. And that's why specializing is a bit of controversy again today with the scientists that are programming their code.
Yeah, one comment about this vendor locking. Yes, this is there is a trade-off to find between programmability and efficiency. So you can optimize a code to death in writing it in assembly, but it will not be portable. And if you want a very general, if you use a very general way of programming, let's say in Python, not naming only this one, but there is certainly other languages, maybe YAML or no, not YAML, Camel. Camel, yes. Anyway, that are not efficient, but they will be very, very flexible. So you can modify it very quickly. So there is a trade-off to find between programmability and efficiency. Maybe libraries could bring it, but vendor locking, yeah, it's a real fear because, well, using NVIDIA CUDA, for example, it's very efficient, but how to move away from it if there is an accelerator emerging from Europe? Well, it will take a long time for the application developer to move to another paradigm. So maybe we should stick with MPI and OpenMP and to have a wait all together to ask for a better programmability of the GPUs with OpenMP.
Okay. Stefano, from your side, would you like to say a few words on this open-ended concern?
Yeah, this is very interesting questions. So, look, we are living in very interesting times with LLMs. Code generation, especially on the higher level of the software stack, is becoming quite cheap. The throughput of code generation, automatic code generation given by generative modeling, many of the tools are improving, capabilities. So I think there will be big changes there. Many companies now are basically rely on LLMs for large part of the software development on LLMs, and the generation of of code and there to have a very disruptive approaches when it comes to to code generation, especially on the higher part of the software stack. Many of these applications have been developed for 20, 30 years. We have a very large range of codes that this LLM can be trained against. So the situation will be quite interesting. No, probably not now, but in 10 years we will probably have we could have technical replacement of all the major code with much better design, much better documentation, and designed specifically for for specific architecture. So the software generation for certain part of the software stack will become cheap, mostly something that you can just consume and throw it away, because the throughput of this is so high. There will be required, some real expert, both for the domain, but also LLMs. So while typically I would say, well, science engineering is very incremental, I think in the next future we will have a quite big surprise, in the way, mostly coming from companies, not academic is typically very slow to react. But I think people will start be preparing to the fact that some code can actually be replaced, and doesn't mean that the knowledge and the code development are for nothing, but will basically feed in this LLM training, to make something better. So I think the future is going to be disrupted, probably not in the way that we're typically thinking, because of these technologies, coming from AI. So it will be disruptive, but we need to be prepared. Understanding technologies, understanding the risk, understanding how we deal with very large code that are automatically generated, for which we might not understand all the details and implication.
Thank you, Stefano. You brought a new dimension to our discussion, that there is this theme of AI for HPC, which sometimes means prediction of results or this type of shortcuts in the computational load. Now you're bringing the aspect, well, what if the software engineering is becoming, let's say, more rapid, again, with a person in the loop, but you see this as a real possibility. This is what I understand when you say. I don't want to ask you to commit to any time frame, but
yeah, I think
even codes like the ones in the plasma and space, etc., which are substantially complex codes, right? You do see an AI-assisted software engineering workflow to be feasible first, right?
yeah, I'm just impressed by two things. First, the current capability, and talking with colleagues, especially education, most of my time, I see some of the coding from the student assisted by AI, going across the spectrum, right? We're talking about FPGA programming, VHDL to MPI, advanced MPI code written. Now, are we still in a situation of delivering probably 50,000 lines of code? We are not there yet, right? Can given a good instruction, can do that today? I think we are in the range. The second observation is the capability of this system are becoming superhuman. It's exponential. So this a new release are come with major leaps in terms of quality, in terms of reasoning. So I see as something that is coming, and the fact that like big companies like Google have it. I don't remember how for a percentage, but it was quite a huge amount of software in Google. So I remember something around 30%, but I don't remember exactly. It's produced by LLM. So this is other risk, but I see that this is going to be in the future. That will be a very different way that we need to relate to this very large code. The reality, you know, is very likely most of these porting to GPUs that we are facing today in difficulty can probably be done being assisted by these LLMs. The quality, you know, for some part is already there, and not only for you know, for developing code, this very large code, but also debugging and making documentation. Is somehow you know, building all this on the huge amount of code that we developed in the past. It's like they're sitting on 20, 30 years of code development. So I see as as something that might happen is as Matteo was saying today. It's difficult to predict the future, but I would prepare for it.
Okay, I think I understand your point. Perhaps from the people on the call, Romain, would you like to say a comment, and likewise Matteo, in any order that you like? Matteo,
Romain?
or Romain, let's
I'm
hear.
here.
Yeah, Matteo, perhaps you can get started, and if Romain has
All right, I will start.
he
All right,
can.
I will start. Thank you. As I said before, I'm not talking on behalf of EuroHPC or the European Union in general. This is my personal and humble opinion about this kind of problem. So as highlighted also by Stefano, I mean, there is, for instance, the LLM are everywhere, I would say, but maybe this kind of code should run in a language processing unit instead of the general GPU. So maybe in the future we should consider to optimize the code in relationship with the specific accelerator. So the accelerator for the language processing unit and this kind of code should be dedicated to a specific, in my humble opinion, of course, to a specific accelerator. And for instance, the tensor processing unit should be dedicated to the stuff that showed Stefano before, so more scientific aspect and so on. This is a general idea. Maybe since the panel is about co-design to meet the future needs in the European HPC ecosystem, maybe also the offer from the ecosystem, the HPC ecosystem in Europe should be improved in order to serve the COEs. Maybe also the policy asset should be addressed. I mean, COE, the Center of Excellence are maybe strategic, I would say, for the Europe. So they should have access to privilege access to the HPC ecosystem. Maybe, I mean, it's something that should be considered. So they could use the computational resources that they need in a quicker way, I would say, and without any problem or without going outside Europe, using the European code in hardware that is outside the European Union, something that maybe we should consider. And as I said, for the code design, I think that we should take into account the new accelerators that are coming, especially the quantum ecosystem that is going, the quantum computing ecosystem that is going to be created. So for that kind of accelerators, specific part of the code should be dedicated. I mean, it's not a general purpose computing. So we needed to start thinking that each accelerator has got his own objectives, his own code, and we needed to try to optimize, since it is the co-design, the topic, then optimize the software and the accelerators together in order to match the two things in order to get a better performance and less power consumption, and also to optimize the use of our hardware that sometimes is not used in the proper way. Because, I mean, for instance, I showed before, the language processing unit should be dedicated to LLM and other code to maybe the GPU or other kind of accelerator. This is my contribution. Thank you very much.
Thank you, Matteo. Romain, do you have audio? Can you?
Yes.
Yes, please go ahead.
Not sure I have much to add, but the discussion about LLMs, they are certainly very impressive, but for some reason, the one quote that I keep being reminded on when I hear about LLMs is the famous quote by Arthur C. Clarke that any sufficiently advanced technology is indistinguishable from magic, right? And I think sometimes we overestimate the power of magic when it is just very advanced technology and not actual magic, which unfortunately doesn't exist. So how much innovation can we get out of LLM versus how much code that looks a lot like code that was needed before can we get out of them? That, for me, the interesting things about LLMs is, are they actually creating something, or are they just, basically finding a middle point in a very, very, very large, in a space, in design space that is very, very, very large but finite number of dimensions, and of which the boundaries of which they cannot push. And so if we need to go to a different kind of paradigm, how helpful can then be? And by that, if tomorrow there is this new way of doing numerical simulation, if somebody find a way to express mathematics in a way that can be easily optimized, like a new improved formula translator, to give it its own name, but it's a new language, can LLMs really be helpful if they have nothing to train on and suddenly they have a new language? Sure, they can figure out the new language and infer things, but can they use efficiently a new paradigm with a new language based on knowledge from previous paradigm and previous language? Because that's something human can do. I wonder if it's something that artificial, not quite intelligence can do as well, or if it's just parroting and rehashing what we have already done as human beings. And for me, that's not a technological question, really. It's how to react to this appearance of magic from a very advanced technology, a very power-consuming technology, in terms of what can it actually achieve versus what we think we can achieve from what we observe as achievements right now. Because all the companies that make a lot of code using LLMs are presumably doing codes that are needed for things that look a lot like what we are already doing. So I wonder, I'm certainly hopeful that eventually it will be able to help us push the boundaries of knowledge, but I suspect that AI can get out of the way a lot of the grunt work, of the basic stuff that need to be done. Generating our messages, that's certainly something that can be delegated to somebody other than me. I won't mind. But when it comes to actually inventing new paradigm, new ways of computing, new way of simulating the universe based on the new science that's being discovered, I suspect we will still need a lot of people to figure out how to do that, and probably do a lot of the work in terms of new area to discover. So I think we still have a lot of work for people like us and for new generation, because and maybe more interesting work, because we will only do what's interesting, which is creating new stuff rather than just having to rebuild a brand new version of the wheel every time so that we can move forward a little bit more.
Maybe I can jump in since I feel guilty. I brought this topic, but my was just, personal opinion when it comes to, should we go, how is the future going to be disruptive? It might be because of this technology that is there. But I would like to go back more to the theme of co-design, like Matteo. I think I share the same vision that we're going towards, to specialized processor, right? And also means specialized application. So we talk about quantum. Now there is, the big wave of making general purpose quantum computing. But also I think we need to do a good job in order not to burn quantum computing, for instance, make people understand that those are machines that remain specialized on simulating quantum mechanics. So yes, there are some application, but where it will shine will be in that direction. And this will, entail, the community, hardware people, to get together. So I share very much the point by Matteo on specialization and identify the right workloads specifically for design. And if it's needed, that's the right direction in order to make computing sustainable, in a smart way.
Etienne would like to say something as well.
Yes, so this discussion is quite interesting and opens some real perspectives. So, that's really fine. And we have to consider the life cycle of the software design, hardware design. And I think it's excellent here to bring around the table people from different horizons and to have this discussion. What I would like to get from the Center of Excellence, for instance, and from the users more generally, is kind of ideas, guidelines, wish list on what should software developers do in their future versions of their software. I think this could be interesting. Vectorization is an example which has been mentioned several times. So have good loops and not bad loops or bad vectors. That's a point. So, but there are certainly other points. And on the other side, what could be the wish list for the hardware to come? So interconnect has been mentioned, so memory as well. So there are certainly many things that may be important and maybe but some kind of bottlenecks right now. So this comes a little bit from this discussion, and I think it's important to continue. Co-design is a kind of Sisypheus effort, which has to be renewed and recommenced regularly. But I think this is a kind of outcome we are looking for. Also, one specific point I did understood is the interest of having some vector for this co-design. This can be at hardware level or simulation. It can be also at software level. It has been mentioned for several COEs, the fact that having some mini apps, relevant mini apps for sure, is quite better than having nothing to really talk about. So having some mini apps permit to show some, I would say, some measure benefit to get some data. So that's something interesting. So this is also a takeaway we may get on this point. So should we conclude now, or is there any?
I just a brief for the mini app. So essentially for us as we work in, for instance, in the Max, the mini app, full app and the mini app, it's a huge difference if you want to do some porting to really something completely new, because that makes the difference whether you need the code developer or you don't need, or the computer scientist or computer engineer can do the entire work. If you have a mini app, it's small enough so you don't have to understand all the physics and all the background. At the same time, the code is not that big, so you can do a drastic changes prove that. So mini apps definitely, slightly decouple the need to have the original code developer and the person that understands the full code, and doing some drastic changes in the data layout and in the everything. So the mini app are proven to be the key. That's the experience we have.
Even if for sure it is not the end of the story, we may imagine a brilliant researcher having some new idea and a completely new approach. But by the way, we need some element to progress. So it's, I think that's one element that may be important.
Yeah. I can comment a bit about what the developer should do and what's their wish list. The wish list is a standard that will help them port easier their application. That's actually the recommendation of Day2.1 software recommendation for the platform. And what they should do is pretty easy. I will repeat what I heard a few months ago from some experienced scientists that have been working on HPC systems. They just are victims of the market. They just need to adapt to whatever is available. So the guy started developing his, I don't remember what field it is, but his scientific application on his laptop. Then he was given 700 Opteron HPC. So he had to port it to the many CPUs. And then he was given a lot of GPUs because GPU was trendy. So he had to port it to GPU. And he's predicting tomorrow, I will have to port it to TPUs because TPU are trending right now. And we will not have the choice because that's what will be on the market. That's what the deciding people will buy. So we just have to adapt again. And that's what Chess should do actually.
Which may be tricky if the TPU are not fit for the real needs.
I mean, in the early days of GPU, they were exploiting OpenGL, shaders that were not programmable using CUDA, and they managed to get speed up. I believe, NVIDIA is already pushing for the emulated flops for having emulated HPL running on tensor cores. They emulate floating point operation and on tensor cores hardware. It's not exactly IEEE 754 compliant. Still, in some cases, it's not deviating. It gives proper, in some cases, not all the cases. And they are pushing for it because they want to remove a few from the GPU to put more tensor cores. So it's a battle high there. And I believe the scientists will find some way to exploit them and to have some nice results with it. It will be more work, more porting, more many things, but do they have any choice?
Yeah, just one word of caution about the mini app. Many of the application developers are, very strong mini apps. They believe that they're not meaningful. So remember, for instance, our Center of Excellence. When we start talking about mini apps or skeleton version of the code, people got the discussion got heated. Then I think in the audience there are a few people, maybe Vasilis, Filippo, and I think as a project we did the right things that what to meet in the middle, right? So between application and explaining is the major interest is to capture all the meaningful part of the codes. So this is something we can do, but we need to engage with application developers because for many of the application developers is it turns out like a more academic exercise, which is not. So we need also to step out from our comfort zone. To meet and discuss about the concern, because I think once it's clarified the concern application developer has, then it goes very smooth. I think in Plasma Pepsi we are doing quite well. But I remember when we start talking about mini apps, there was very strong opinion. So it requires little engagement from all the parts, and keep in the loop all these application developers and feedback and how the how the feedback can happen from the big application to the mini apps to get improving, becoming more meaningful.
I tend to agree that mini apps are very useful for studying some certain aspect of an application, but the ultimate truth is in the code as it is run in production. That's what is important eventually, ultimately. So mini apps can only be a proxy to understand those aspects and improve them in an easier to manage way.
Sure.
And one recommendation I would make to developers is to keep track of performance in the same way that they keep track of functionality via non-regression testing and similar methods. And that being able to track on reference test cases, not just the overall performance, which can hide a lot of problems by averaging them, would be to keep track in the long term of profiling of the application on non-reference hardware, so as to be able to identify when performance regression appear, when performance is really improved for some aspect, even if overall in the application, the averaging effects means that it's not that great, between ML's low and the fact that improving one part might degrade another. Because understanding the application also requires to understand performance on when you change the version of the compiler, when you change the compiler, what is happening. Because when we do detailed studies of such things, sometimes two apparently similar behavior in terms of overall performance is hiding that different compilers, different platforms are very different strengths and weaknesses. And that only by studying the application in differential analysis between different version in time, different compiler on the same version, different platform with the same code on the same compiler, can you really start understanding what is impactful in terms of performance on an application.
Okay, thank you, Romain, for this point. I would like to thank the panelists, particularly for tolerating the delay that we had during the session. We got a lot of value out of your positions, and we appreciate particularly the time of the people on remote that had to wait us until the panel got started. We will try to collect the materials and share them with the audience of this event. We are grateful for the people that took the time actually to travel, be on site. We were happy to have you here at Fort. And I think that all of you got something to think about. If this is enough, plus a bit of sun and, vitamins and such, I think this is a successful trip. I would like to pass the microphone to Etienne to wrap up the event for us.
Yes, I will add my thanks also to all of you for your time, your attention, your contribution to Force for hosting this event. Thank you, really. I think it was interesting, and I hope you have some takeaways and some thoughts after those discussions. So it's time now to wrap up, to conclude. So what I will mainly do is to invite you to join us to our forum in 1 month's time. It will be the opportunity to continue some of the discussion we have here. I think it's interesting. And then the suite will be in further projects. So we have there that has been presented, other to come. So I think then we will approach the end of API project. But a big thank you to all of you. And let's see you soon, hopefully. Thank you.
Thank you, everybody. Bye-bye.
Thank you all for attending. We are wrapping up the session here.